Hello everyone, I'm Somil and I'm an assistant professor in the Aero department here where I lead the Safe and Intelligent Autonomy Lab. I will just wait for the slides to go down. All right. So let me start this talk with the long-term goal of our lab, which is to develop robot algorithms that operate with guaranteed safety and performance in new and uncertain environments. And we think about this question in the context of a variety of different applications, autonomous drones, autonomous cars, Lego robots, aircrafts, and more recently, space exploration. And if you look at these systems, machine learning and AI are becoming increasingly pervasive in their autonomy stacks, most notably for perception and trajectory forecasting, but also for planning and control. And for a number of good reasons. Machine learning is really good at capturing the complexity of real-world situations that this system must operate in, which could be otherwise very hard to capture using engineering domain knowledge. But inclusion of machine learning has also come up with some new safety challenges for these systems. So we are right in the Bay Area, where we hear news such as cruise cars are being rolled back from San Francisco City, or robots are crashing into humans on the factory floors. The issue is severe enough that the US government, and since then many other governments, have passed executive order to prioritize discussion on AI safety, both for autonomy, but AI more broadly as well. So there is this tension that we have a lot in autonomy today, which is how can we enable these systems to leverage the capabilities and excitement offered by modern machine learning methods while also maintaining safety. And in my talk today, I want to think a little bit about the source of this tension and what can we do about it. So I think one of the main reasons for this tension is that if we look at machine learning systems today, most of them are designed without any specific regard to safety. And when safety issues emerge in the design system, post hoc solutions are often engineered to counter these risks. So I am going to refer to them as safety bandages throughout my talk. Right, so as an example, earlier this year, in February, I think, Waymo cars had a bunch of troubles with, for example, tow trucks. So the approach was to shut down the entire fleet of Waymo, update their software, and then restart the fleet. Now, while this approach makes the design of learning-based systems much simpler, it is flawed for a number of key reasons. Now, first and foremost, these hand-engineered solutions are simply not scalable with the number of safety risks and the situation this system must encounter. Moreover, these post hoc solutions often tend to be conservative in nature, which might degrade the performance advantages that we get out of machine learning methods. And finally, the heuristics designed for some certain kind of deployment conditions might not work as the systems encounter new and new deployment conditions in the real world. So to overcome these challenges, in our research, we think of safety of learning-based systems as a continuous process where safety is formally ingrained in different stages of the learning process, starting from the design and training phase to their deployment to iteratively improving the safety over the system's lifecycle. So what that means is that we develop algorithms that programmatically incorporate safety requirements in the training process itself in order to learn inherently safe and robust controllers and policies for robotic systems. Now, that I would call design time safety methods or design for safety. Now, that's definitely a step forward, but that's not all. Because as these systems will operate in new conditions, they will need to adapt their behavior. So we are developing methods that detect out of distribution and anomalous situations for these systems and correspondingly adapt their behavior in order to maintain safety. And finally, we want these systems to learn from their past failures, past mistakes. We don't want the system to make the same mistakes again and again. So to close this loop, we are developing methods that allow robotic systems to improve their safety from their past failures. And so together, I think of this as a closed loop. I call it continual safety assurance framework, where assurances are provided provisionally during the design time. They are monitored and adapted during the operation time, and they're continuously improved over the system's life cycle. So in the remaining time that I have, I want to dive a little bit deeper into some of my work. So we will start with talking about how can we learn provably safe controllers from data. How can we adapt these controllers online under new deployment conditions? And finally, I will talk about how can we stress test a given policy or a given controller to mine its safety critical failures. So let's talk about learning safe controllers. But even before we talk about that, let's take a step back and ask ourselves, what do we even mean by safety? What do we want out of this safety analysis in an ideal world? And I thought about it a lot, and I tried to summarize my thoughts in a single sentence. And so this is my attempt at that. I would say, out of safety analysis, we want to determine whether and how a robot can prevent its trajectory from entering into some undesirable set of states, which I will also refer to as failure set. And so what that means is that we want two key things. First, we want to quantify which configurations of the robot are doomed to fail versus which configurations are safe to be in. And how can we keep the robot in these safe configurations? So first is the problem of whether the system is safe, and the second is how can I keep the system safe? So I like to call it whether and how of safety, and I will refer to as that throughout my talk. Now, the good news is that control theory provides us a number of powerful frameworks for doing the safety analysis of autonomous systems. And in our work, we use one such framework quite frequently, which is called Hamilton-Jacobi reachability analysis. And the reason for that is that not only it helps us to mathematically characterize these two requirements, but also provide a mechanism to automatically compute them. So let me spend the next few minutes talking about what Hamilton-Jacobi reachability analysis is, and then I'm going to come back to the question of learning safe controllers from data using reachability analysis. Okay, so in reachability analysis, we assume that the underlying robotic system has some dynamics F with state X, control U, and disturbance D. So disturbance here represents uncertainty in the system, for example, modeling error or unmodeled effects, or an actual adversarial agent that we may want to safeguard against. Now, given these dynamics, the key thing that we are interested in is the backward reachable tube of the system, which is a set of all initial states from which the robot will be ultimately driven to an undesirable set of states or a failure set despite the best control effort. So essentially, backward reachable tube represents the unsafe configurations for the robot and should be avoided. Let's try to understand that with the help of a very simple example. So imagine a quadrotor moving longitudinally up and down in this room. So here the ceiling and the floor might represent the failure set that we don't want the quadrotor to crash into. The light red region over here is the backward reachable tube, meaning that if the quadrotor starts inside this set, then no matter what it does, it will eventually crash into ceiling or the floor. So there is nothing you can do to avoid the collision. In other words, these states are as doomed as being in the ceiling or the floor. The contrast of this light red region is the blue region, or the safe set for the system, meaning that if the quadrotor starts inside this set, then it has a controller or a policy to keep it inside this set at all times. So reachability analysis will give us both this blue set as well as this safety controller. So I'm going to dive a little bit into the math of reachability analysis and how it computes these two entities. And the first step to do so is to define our failure set implicitly with a function L of x, which is negative inside the failure set and positive outside. So you can think of L of x as the safety reward the robot gets at state x. If you're inside the failure set, you get a negative reward. And if you're outside the failure set, you get a positive reward. And we can use any reward function that satisfies this property, but the one that's quite popular in robotics is the sign distance function to the failure set, which is naturally negative inside the set and positive outside. Now, given this reward function, the cumulative reward of the trajectory is given by the minimum safety reward along the trajectory. So this is slightly different than our normal optimal control and reinforcement learning problems, where it's sum of rewards. Instead of that, it's the minimum of reward. And what that means is that if the robot trajectory ever entered the failure set, this cumulative reward will be negative, otherwise it will be positive. So just looking at the sign of this reward, I can tell whether the system trajectory was ever safe or not. And then, of course, we have control at our disposal. So what we want to do is we want to formulate this game between the control and disturbance, where the disturbance attempts to force the system inside the failure set. In other words, it tries to minimize our safety reward, whereas the control tries to stay out of the failure set. In other words, it tries to maximize the safety reward. And Similar to any other optimal control or reinforcement learning problem, we have a value corresponding to this gain, which is simply the control maximizing it and the disturbance minimizing this overall cumulative reward. Now, intuitively, this value function is capturing the closest the system will ever get to the failure set. So if the value function is negative, that means the system must have entered the failure set at some point. And if the value function is positive, that means the system remained outside the failure set at all times. So the backward reachable tube that I described earlier, or the unsafe set, is nothing but the set of states where the value function is less than or equals to 0. So that's the idea of reachability analysis. Now, this value function can be computed using the principle of dynamic programming, which results into a Bellman iteration or a Bellman backup. But in continuous state and time, this results into a partial differential equation. So this is just the Bellman equation written in continuous state and time, honestly. But just like the Bellman equation, essentially it relates how taking a particular action affects the system value, or in other words, how system distance to the failure set in this case. And once we solve this partial differential equation, which is called, by the way, Hamilton-Jacobi-Isaacs partial differential equation, we get the value function. So here I'm showing that value function for the quadrotor example that I was showing earlier. The more red means the value function is more negative, and the more blue means the value function is more positive. So these states, which are closer to the ceiling and floor, not surprisingly, are particularly bad, whereas the states which are towards the middle of the room are very safe, as you would expect, because we are sort of equidistant from the ceiling or the floor. Now, quick question. The value function is more negative towards the lower end than towards the positive end, even though the failure set is both ceiling and floor. Could you guess why? Gravity. Because of gravity. Because gravity is pushing us more in one direction. So when we are closer to the floor, we are more unsafe than we are when we are closer to the ceiling, which is what this value function is capturing inside this color bar. But the beauty of the reachability analysis is that this is an intuitive example, but that's not where it's meant to be. It automatically captures the effect of the dynamics of the system on the overall safety of the system. Now, along with this value function, it also provides us a safety controller. Safety controller, which, again, intuitively what it is doing is that at any state x, it's pushing the system towards higher and higher values. Remember, positive values means more safe. So it's essentially pushing us in the gradient ascent direction of the value function. That's what it's doing. Okay? So, taking a step back, if you recall, I said there are two key things we want out of safety analysis: a set of safe states and a controller to keep me inside the safe states. I was talking about Hamilton-Jacobi reachability analysis, which sort of captures these requirements with the help of the safety value function V, whose sign tells me whether I'm safe or unsafe, whose gradient tells me a safe controller for the system. And once again, the nice thing about this theory is that it can be applied to general nonlinear autonomous systems. But there are also a few challenges. The biggest one is scalability. So even though the theory is quite general, computationally speaking, it is very hard to scale these methods beyond even 5-dimensional systems, which really limits their sort of use case in the modern robotic systems. And the second, which is equally bothersome, is that it's not immediately clear how to interface these methods with real-world data and machine learning models. So to begin making progress on these challenges, we will lead into neural approximations of the safety value function. Now, of course, we are talking about safety critical system, so we have to be a little bit careful when we are using neural network, and I share that concern as well, and we will talk about it. But for now, I want to put guarantees on hold for a minute and talk about how can we even structure the learning problem in order to learn good representations of safety value functions. And then I will come back and talk about assurances under these representations. So more specifically, we will learn a neural approximation of the safety value function, which takes as input the state and time of the system and output the corresponding safety value function. Now, once trained, this value function can be used to synthesize the unsafe set as well as the safety controller using the same mechanism that I just described. But okay, how do we obtain this value function? So we call this method deep reach. And deep reach is a self-supervised learning method, which relies on the fact that the true safety value function must satisfy this partial differential equation that I showed earlier. So the partial differential equation error can be used as a signal to train the safety value function. In particular, in each training iteration, we can randomly sample some state and time. We propagate it through the neural network to compute the value function, and correspondingly, we can compute the PDE violation error. And we can backprobe from that to optimize the neural network parameters. So essentially, over time, neural network is incentivized to learn a more and more accurate representation of the safety value function that is consistent with this partial differential equation that I said earlier. So it's very much inspired by physics-informed machine learning these days. Okay, there are two key advantages of doing that. Number one is that by doing so, we can explicitly bake in safety requirements in the training process itself and learn inherently safe controllers from data. And second, the neural representations are much easily scalable to higher dimensional systems, so we can synthesize safe controllers for a broader class of autonomous systems. So let me show a few examples of that. So the first example here is the 3-aircraft conflict resolution problem. There are 2 evader vehicles, and there's a pursuer vehicle, which in this case is an uncertain or adversarial aircraft whose behavior we don't know, so we're going to treat that as a disturbance in the system that we want to safeguard against. Now the failure set here is given by any configurations of these 3 aircrafts which are where any 2 aircrafts are in close proximity of each other. In other words, something called loss of separation. Now given the high dimensionality of this problem, a direct BRT computation or unsafe set computation is not scalable in this case. So what is often done in multi-agent literature is that people compute pairwise collision set between these aircrafts and take their union as an approximation of the unsafe set. So I'm going to show you a slice of that 9-dimensional set in 2D in green over here. And what that means is that if I start at any configuration inside this set, then at least 2 of the 3 aircraft will come into close proximity of each other. In other words, they will collide. But with deep reach, we can directly compute the high-dimensional BRT, and a slice of that is shown in the pink over here. So of course, it captures the green region, but it has some more additional configurations that we could not capture earlier because of the computational limitations. So let me show you one such configuration and see what's going on here. So let's pick this configuration. So starting from this configuration, I'm plotting the trajectories of the 3 aircrafts. And here you see that the orange vehicle is going after the blue vehicle. And the blue vehicle is able to avoid the orange vehicle, but in the process of doing so, it cannot avoid a collision with the black aircraft above. So there are these 3-way interactions that are happening between the aircrafts, which we could not capture earlier because of the computational limitations. But now we can not only capture them, but we can safeguard against them using the deep reach-based safety controllers. We have also applied this framework in the context of autonomous driving. So this was inspired by my work at Waymo, which at the time was dealing with urban driving. So San Francisco rolled out, hasn't happened yet. And one of the big problems was that there were a lot of stranded vehicles you encounter in urban driving. So this could be, for example, an Uber or a trash truck waiting in your lane, blocking your lane. And in this case, the autonomous car needs to go to the other lane, cross over, and then come back to its own lane, but in a way so as to not collide with the oncoming traffic. So we started with a learning-based controller, and it performs really well, except that it was not able to always capture this nuanced intersection point between the 2 cars and leads into collision like over here. But with deep reach, we can now additionally bake in the safety requirements directly in the learning process. So let me show the behavior of that controller in the car icons over here. So what it does is that it actually pushes the white car a little bit towards the stranded vehicle and make the orange vehicle swerve so that a clearance is formed between the 2 vehicles. And once they cross each other, they go back to their respective lanes. But what is particularly interesting is that the behavior of the safety controller automatically adjusts to the oncoming traffic. So for example, if the orange driver is very aggressive, the safety controller makes the white vehicle wait behind the stranded vehicle, let the orange vehicle pass, and then go over and cross the lane. And if you think about it, this is how intuitively we will drive in these situations, except now these behaviors emerge automatically out of the learning-based system because the safety requirements were baked into that. And in our latest work, we applied deep reach for learning safe controllers for legged locomotion. Here, the safety problem is a little bit more challenging because it's a hybrid system. It has both continuous controls, but also discrete controls coming from different working patterns. And here, safety controller reasons about different working patterns in order to reach its goal without colliding with obstacles. But what I find exciting is that my student Shuang here is deliberately trying to push the robot into a collision, but the safety controller counteracts to this external disturbance and sometimes even changing its working pattern completely in order to maintain safety. Okay, so when I was starting to discuss deep reach, I said, let's put guarantees on hold for a minute. So let's go back to that, and let's talk about how can we provide safety under these learned representations. So now, as such, neural network can make errors, and the safe set provided by deep reach is only a candidate safe set. Pictorially, there could be actually states inside this candidate safe set which eventually might steer the system inside the failure set. So to counter this problem, we have been looking into probabilistic safety assurances for deep reach. So I will talk about what that means in a second. But the key idea behind this whole probabilistic assurance is that the learned safety value function induces a candidate safe policy for the robot as well, which if I apply on the system should ideally achieve the same value as that what deep reach was trying to learn, because that's what it means to have the value of a policy, that you should essentially, if you roll out that policy, you should achieve the same value back. So the gap between the two value functions can actually be used to calibrate the learning error. In other words, I'm interested in finding a bound on the maximum learning error, which is the one predicted and the one I get by rolling out. And if I can compute this bound, then I can simply correct my value function by this bound. Pictorially speaking, if I look at any states in the super delta level set of my value function, then that state would remain safe under the induced policy by deep reach. So then the last thing that we need to do to provide assurances is to compute this bound delta. And we have looked into a number of different ways to compute this delta, including neural network verification methods, scenario optimization. But the one that I am particularly excited about, and I'm going to talk about today, is conformal prediction. And for that, there are two reasons for that. Number one is that it's sort of beautiful because of its simplicity. And second, it can easily handle inputs of varying dimensions. And that's what we are primarily interested in, high dimensional control. Now, ultimately, what conformal prediction provides is a probabilistic bound on delta. So it cannot compute the bound delta exactly, but it can compute a high confidence bound on delta, which looks something like this. So we get some Q hat from conformal prediction, such that the probability of failure in the super Q hat level of the value function is below epsilon. So essentially, we are getting a high confidence safe set after correcting this value function using conformal prediction. And I just want to illustrate that method in the context of this multi-vehicle collision avoidance problem that I was showing earlier. So yellow is the learned backward reachable tube. The blue is the correction by conformal prediction. In this case, it turns out to be 0.1, which gives me the certified safe set in green. And in this case, epsilon is 0.001, which means that any state inside the green region is at least 99.9% safe. Okay, so let me summarize this first part of my talk. We talked about neural safety representations that combine the rigor of traditional safety analysis methods such as Hamilton-Jacobi reachability analysis with the dynamic learning capabilities of AI. And it has two key advantages. The first one is that This allows us to bake in safety constraints in the learning process. And second, these methods are much easily scalable to higher dimensional systems. But so far, my definition of what is safe or what is unsafe is not changing, and everything about this system is known a priori, whether it's dynamics, whether it's control bounds, and whatnot. But that's not true in the real world. In the real world, you will constantly encounter changes in your safety constraints, in your dynamics, in your control authority, or in your environment. And as the system learns more information about its world, it needs to dynamically adapt these safety controllers to maintain system safety. So that's what I'm going to talk about for the next 5-10 minutes. How can we adapt these safety controllers online very quickly? So one of the exciting aspects about neural safety representations is that you can easily input additional data to the neural network. For example, uncertain system or environment parameters, and learn the safety value function as a function of these parameters. So we call it parameter condition safety value functions, just because they are also now additionally conditioned on beta. What's the advantage of that? Is that offline, if you learn this parameter condition value function, online, you can quickly activate the safety value function corresponding to the deployment conditions you encounter in order to maintain safety. So let me show you that on a very simple drone delivery problem. So here the drone needs to go to its goal location while avoiding collisions with the obstacles on its way. But it needs to do so in uncertain wind conditions. So we don't know what wind intensity it's going to encounter when it's going to go out for delivery. So we learn parameter conditions value function as a function of the uncertain wind intensity. And here I'm showing you the safe set corresponding to the low wind intensity. So what that means is that if the quadrotor starts inside this blue set, then it can reach its goal safely without colliding with obstacles. So when the drone started, the wind intensity was low, so it goes on to take a more direct route to its goal location, which is through these narrow gap, which makes sense because it would be more efficient. But on its route, the wind conditions change, and now the wind intensity is high. So the safe set changes. Now this middle route is no longer safe for the system under this high wind intensity. But using this parameter condition representation, we can quickly adapt our safety controller, which in this case goes on to take a longer but safer route to its goal location. In fact, we don't have to stop at just parametric changes. We can now think about adapting safety value function directly from high dimensional observations, such as RGB images or LiDAR scans. For instance, here, this robot dog is dynamically constructing its safety value function directly from these raw LiDAR scans and using it as a safety layer on top of an RL-based policy to maintain safety in this unknown environment. So not very innovatively, we call it observation condition reachable set instead of parameter condition reachable set. And there are two key adaptation components here. The first one is that the robot using this LiDAR scan to dynamically adapt its safety value function, which allows it to adapt to unknown obstacles that it's going to encounter in the real world. There's a second adaptation component, which is allowing it to constantly estimate the uncertainty in its own dynamics, for example, due to rugged terrains or slippery surfaces that you might encounter, and correspondingly adapt the safety value function using the idea of parameter condition reachable set. So it's combining both of them together to ultimately get the safety value function, which is then used as a safety filter for a nominal policy. So let me highlight the uncertainty estimation component a little bit more. So in this video, the robot encountered this slippery patch. And as the robot enters the slippery patch, the uncertainty estimation in its dynamics is high. Correspondingly, if you look at the safety value function, it becomes more conservative, so more red meaning more conservative, and it slows down the robot in order to avoid a collision with the obstacle in front. So of course, there is also adaptation going on based on LiDAR, but I'm only highlighting the uncertainty component part here. So this is the kind of adaptation we can enable in real time on robotic systems. In fact, this framework is completely agnostic to what underlying nominal policy are you using. So here I'm using it as a safety layer on top of several different RL-based policies, such as RMA, Work These Ways, as well as MPC-based policy in a variety of different environment terrains, dynamic obstacles, and adversarial humans. Again, the key component here is to be able to adapt to dynamic obstacles or unknown obstacles and the environment uncertainty, which is what the neural safety representations can enable us to do. Okay, so far I've talked about designing neural safety representations and adapting them online corresponding to the changes in the system and its environment. Now, for the remaining time, Anna, I want to focus on the reverse direction, which is, suppose you give me a learning-based policy. So far I was designing learning-based policy, but now suppose you give me, it could be, for example, an RL-based policy. How can we stress test this learning-based policy to figure out the data regimes where it might cause safety-critical failures of the system? And we have been particularly interested in stress testing vision-based controllers for two reasons. A, because they are becoming increasingly ubiquitous in our autonomy stacks, but also they have been traditionally been very challenging to handle using traditional safety analysis methods because of their high dimensionality and complicated nature of visual inputs. So let me formalize the problem a little bit. So once again, we have a robotic system with some dynamics. And at each state, we have a visual sensor which is giving me visual observations such as an RGB image or a point cloud, which is taken as input by a vision-based controller that gives me the control to be applied on the robot. I'm also given a simulator which I can use for stress testing this system. My ultimate goal is to figure out the set of images or point clouds I, which lead to the failure of this overall closed loop system. So I'm very specifically interested in finding I's that leads to the failure of the system, not just the vision-based controller. And what we do is we cast this failure discovery problem as a reachability problem and use the corresponding backward reachable tube to extract these visual failures. So let me explain how we can do that. Well, we can cascade the robot sensor function along with its vision-based controller to obtain an equivalent state-based policy for the robot. Right? Because X goes to I goes to control, so if I combine the two, it goes from X to U. And so I can simplify, for the purpose of stress testing, I can simplify my closed loop as the system in closed loop with this augmented policy. And we know how to find failures of such systems. That's what I've been focusing on the first half of my talk. We can compute the backward reachable tube, which generally give me the set of all states which will lead to the failure despite the best control action. But in this case, I'm not interested in the best control action. I'm interested in a specific controller that's given to me. So I can just simply replace this max U by that specific controller. But with this minor change, I can use the same reachability tools that I've been describing so far to compute this backward reachable tube. So you can think of this as a policy condition reachability, if you will. So once I get the backward reachable tube, then I can look at the images seen by the robot along these failure states, which will give me the visual failures for the system. So let me explain that in the context of an example. So this work was done in collaboration with Boeing, which designed a vision-based controller for the autonomous aircraft taxiing. So the goal here is to keep this aircraft on the runway only using the monocular RGB images from the camera on the right wing of the aircraft. Because they were testing what happens to the taxiing process if there is no GPS. So they were trying to test these vision-based policies. But in the process of doing so, we don't want the aircraft to leave the runway. So that's my failure set in this case, outside the runway boundary. Now, using this proposed framework, we compute the backward reachable tube of the aircraft under the vision-based controller. So in the red are the starting configurations of the aircraft from which it will be ultimately driven to off the runway under the vision-based controller, whereas the blue means the safe configurations of the aircraft. And here are some of the representative images that gonna cause the failure. Excuse me. So let's take a look at this image and see what's going on, why it's causing the failure. So I'm just showing that picture again. So this is the first-person view, which is what aircraft sees to make the decision. And upon the analysis of this image, we found that actually vision-based controller confuses this runway markings with the center line of the runway. And it drives the aircraft towards that marking. By the time it realizes, no, it's not the center line, it's already too late, and it caused the aircraft to leave the runway. So using the proposed framework, we can find such semantic failures of the vision-based controller. And I want to highlight that these are not just any semantic failures. These are precisely the failures of the vision component then that lead to system-level failure. So for instance, here I'm showing you the prediction error of the vision-based controller. The red means high prediction error, and the blue means low prediction error. And you can see there is a whole bunch of states where the prediction error is high, but that doesn't mean for safety anything. The system is still going to remain safe. So there's a component-level failure, but not a system-level failure. Conversely, there are a whole bunch of states where the prediction error is really low, but that is enough to trigger a safety-level failure, or system-level failure, sorry. So we are particularly targeting those component-level errors that then lead to system-level failures. And we can now combine this with the idea of parameter condition reachable sets to obtain these failures as a function of different environment latents, such as the time of the day or cloud conditions. So for example, the same state which was failure during the morning time because of this runway marking is actually safe during the night time, which is very counterintuitive because most of the vision controllers are going to downgrade when they are operated in nighttime because of the low visibility. But because of this semantic failure, actually this state is no longer a failure in the night, and we improve the safety of the aircraft. And similarly, we can find the failures as a function of cloud conditions, and we can get a diverse set of failures of this system. Let me show another example. So this is an autonomous indoor navigation pipeline, which has a perception component that takes as input the RGB image on the robot to output a waypoint, which is then tracked using an MPC-based controller. This framework was trained entirely in simulation, and here is a run of that controller in the real world. And it works quite well, actually, even though the robot has never seen this environment before. Only using the first-person RGB image, it is navigating through this very cluttered hallway with bikes on one side and cubicles on the other side in order to reach its goal safely. This is my bike, by the way. I used to sit here 5 years ago when I was at Berkeley. But there are a lot of interesting failure modes of this controller that we found using the proposed framework. In the interest of time, let me just highlight one of them. So we learned that the vision-based controller here learns a correlation between light-colored surfaces and traversability. And the reason for that is a lot of the training data, or the majority of the training data for this controller, has actually light-colored floors. So the vision-based controller somehow learned this spurious correlation that whenever there's a light-colored surface, I can go through it. During the test time, when you encounter light-colored walls, it thinks it can go through it too, resulting into a collision. So once again, we are trying to figure out those failures of vision-based controller, then ultimately leads to the system-level failure. But why am I doing this? Where I'm going with this? Well, if I know the failures of a vision-based controller, I can use it to improve the vision-based controller. That's the ultimate purpose. For example, I can use these failures to train an anomaly detector, which given an image, tell me the probability of failure of the system. And if this anomaly detector triggers a fail, then I can use a fallback controller, for instance, to preserve the safety in an online mode. So this is the same scenario as before, where the aircraft was failing because of this runway marking. But now you will see that anomaly detector flags that as a failure input. So it slows down the robot, which is what fallback controller is doing. And then once we cross the pedestrian crossing, the runway marking, we goes back to our learning-based controller and then maintain system safety in that way. This is very preliminary work. Of course, there is a lot of interesting questions here, which is how do you design the anomaly detector? How do you design the fallback controller on that anomaly detector? These are very interesting questions, but But this is what a catalog of failures of the system can at least give us as a starting point. We can also do something more. We can try to do the targeted incremental training of this controller on that failure data, and that should improve our performance. So for example, in the gray is the BRT before the incremental training, and the blue is after. And you can see how there is a significant reduction in the unsafe volume. Okay, so let me take a step back. The key goal of our research was to design autonomous systems that can leverage the capabilities offered by modern machine learning methods while also maintaining safety. And towards that goal, we think about safety in different stages of the learning process, starting from the design to their approach to their operation to offline testing. And today in particular, I touched upon a part of our research, which is neural safety representations that can enable operationalize such a framework. I have a few more minutes, so let me just quickly highlight some of the other projects in the lab without going into too much detail. So I talked about deep reach, which is one paradigm to learn controllers for robotic systems, but there are many other interesting learning paradigms that have been shown very promising results. For example, imitation learning. And so we've been asking ourselves, how can we learn safety-aware imitation learning policies, in particular behavior cloning policies? And from a safety viewpoint, one of the problems with imitation learning is that it suffers from compounding error problem or covariate shift problem, which means that even if you give safe demonstrations to the system, there's no guarantee that the resultant policy will be safe for the system. So to think about this problem, what we have been doing is we have been injecting this adversarial disturbance in the system during the data collection procedure. So this adversarial disturbance is computed also using reachability analysis, but it is doing exactly opposite of what safety controller does. Rather than pushing us away from the safety critical states, it's going to push us towards the safety critical states. So it's going to do the gradient descent instead of gradient ascent on the value function. And by doing so, our hypothesis is that the robot gets to visit more safety critical states, and we can learn corrective actions from those states. So now during the test time, so once we collect that data, we train the behavior cloning policy using the same methods as we do for the rest of our behavior cloning policies. But during the test time now, if the policy makes an error, and in particular if the policy makes a safety critical error, then hopefully it will be able to better recover from such states. So that's the hypothesis. Let's see how it plays out. So this is the same aircraft taxiing problem that I showed earlier. Here's the imitation policy, which goes from image to action. And over here, I'm showing you the percentage failures across a bunch of test trajectories for the vanilla behavior cloning and the safety-aware behavior cloning for different number of demonstrations. And you can see, even with a handful of demonstration, injecting this safety information significantly improves the safety of the test, safety of the policy at the test time. And to understand why, here I'm showing you the demonstration as well as the rollout of the policy for the vanilla method and then our method. You can see that for the vanilla behavior cloning, as soon as the policy makes errors, in particular, as soon as it starts going towards the boundary of the runway, it cannot recover from it because it hasn't seen much data on those states. On the other hand, with the safety-guided imitation policy, we are particularly pushing the system towards this runway boundary in this case. And so it can learn recovery behavior from such states, which then reflects in its test time performance. And to clarify here, the data used for the both methods are exactly the same. We have also applied this on a real crazy fly. And once again, I think the story is the same. With only 5 demonstrations, we are able to do much better sim-to-real transfer, specifically when we think from a context of safety. And in fact, I believe that there is something more here. This idea of using safety-critical information can be useful to guide the exploration of our learning agent more generally, in my opinion, in order to design more robust policies. So for instance, here we are using the safety information to guide the exploration of a sampling-based planner, in this case MPPI. And you can see how this signal is helping the planner to explore more relevant parts of the state space. Earlier, I was wasting a lot of samples in the obstacles, but those are useless samples. Those are never going to improve the performance. So if you can guide them in the right direction, then I can achieve the same performance with much fewer samples. So safety can also help with exploration during the design phase, the direction that we are actively pursuing in our group. And then the another big challenge in safety today is who gives you these safety constraints? Who tells you what is safe, what is unsafe, right? And that's a big question. Luckily for many of FAA applications, well, FAA gives us, but in robotic systems, that is not clear. So we have been thinking about how can we use language as a medium for somebody to flexibly define these constraints to us. So for example, in this picture, as my robot is going through the lab, can I communicate to the robot that avoid the coffee spill on the floor? And so we have been using vision language model to convert this natural language feedback into certain physical constraints that are more interpretable by traditional safety analysis methods, such as reachability analysis or control barrier functions, in order to design a safety controller that adheres to these natural language feedback. And here is a very simple experiment of that. Here you will see the safety constraints given by the user, and we're using VLM to convert that into a safety constraint and then correspondingly computing a safety controller. And so now the robot is given this constraint, avoid the coffee spill, and sorry, it actually doesn't slow. It doesn't actually stop. Somehow video was laggy here. And so this is nothing fancy compared to what we can do with VLMs and LLMs today. But this is a starting point to think about how these tools can be used to define these rich safety constraints and semantic safety constraints for our robotic systems. Okay, so let me stop here and thank all my collaborators and my students who actually did the hard work. I'm only doing the PR here, as well as our sponsors for funding our research. And I'm happy to take any questions.
So I have some questions about learning the value function about safety. So for the parameterize, that kind of neural function, I felt that for different betas, I thought that we already need some kind of data already obtained at certain beta parameters. But I believe for the kind of wind example, I think it's kind of realistic because we can try multiple experiments in multiple wind conditions. But for observations using LiDARs, I felt that it must be really hard to get almost every data from many observations. So you mean if we are using parameterized neural learning, it's some kind of interpolating the beta values to get better.
Yeah, so in that LiDAR example, you can think of beta as not being explicit parameters but latent parameters. So the LiDAR scan is going into, in this case, a graph neural network, which is giving me some latent representation of that as the output, which is then taken as input by the safety value function. So beta could be explicit physical parameters, but they could also be latent parameters.
Also, you mean for some kind of really sophisticated or complex input for beta, you can some kind of do pre-processing to make it representation.
Yes. You can do encoder-decoder kind of frameworks, or you can do simultaneous learning as well. Okay.
So how does the complexity of deep read scale with the dimension? Like I know obviously HAR in general scales very poorly, but how does deep read scale?
That's a good question, and I think the scalability is or what it scales with, I guess, what the computational complexity scales with as in is not immediately clear. Let me start there, because I can certainly give you two-dimensional example where the value function is really complex and it will be very hard to learn that. On the other hand, I can give you 1,000-dimensional system where it will learn it within 10 minutes. So what I guess deep read is betting on is that if the value function that you're trying to approximate or trying to compute has a lower dimensional manifold that you can learn easily, then you will have a better time. There is no magic here, so it cannot overcome the curse of dimensionality for good. It's only relying on the fact that for many systems of interest, there is a lower dimensional representation of the value function. And so by not relying on grid-based computations, you can overcome some of these challenges.
And does that also imply that there's smarter gridding ways to do general, like, vanilla HAR?
I think so, yes. Okay. Yes, there should be. Because I think of grids as also a parametric representation where the number of parameters is equal to the number of grid points. That's one way to think about it. It's also a function of approximation if you take that angle on it. So you're just using way too many parameters, perhaps, than you need to.
So he showed like a slide where you're like training like a vision-based controller based on the anomalies that you detected. So my question is that if you take that vision controller to, let's say, another runway, will that, incrementally trained network perform well there? Or will it like have some sort of like overfitting issue?
That's a good question. And in fact, before even overfitting, Rohan and I were chatting about it a couple of weeks back, but one of the issues we see with incremental training is that you might now start seeing failures in certain regions of state space where you were fine earlier. Because if you look at it today, we don't have machine learning methods that lead to monotonic improvement as you get more data. So if I give you data set 1, say D1, and I add 100 more samples to it, so D1 plus 100 samples, there's no guarantee that when you train it on D1 plus 100, the performance will be completely monotonic over D1. And when I say completely monotonic, meaning point-wise monotonic over D1. Of course, in overall metric, in aggregation, it could be true. It probably is true, but not point-wise, which matters for safety, which means that the BRT volume now has some intersections with the previous BRT, and it is smaller in some other regions, right? So actually, incremental training is very hard to make work in a monotonic direction right now. So absolutely, it will fail in some other runways.
So it's like even if you like take it to another runway, it might fail where it was like performing well at.
Yes, even on the same runway, on the same configuration, it might now perform worse.
Okay.
Because incremental training doesn't guarantee a monotonic improvement in the safety. So yes, that's one of the questions we have been thinking about in our lab, which is how can we lead to monotonic improvement in machine learning models as we increase more data. Yes.
How do you handle situations when there are states which are unsafe or close to the unsafe region but also yield high rewards? You would want to be there but also not want to be there.
It's a good question. So one thing that I completely brushed off is, so far I've only talked about safety, right? But that, of course, a car that is sitting in my garage is the safest car ever, but we don't want that. So how to sort of co-optimize safety and performance? And current methods, unfortunately, to do so are fairly myopic. The popular scheme being safety filtering that I was describing, which sort of does it on a point-wise basis. So it doesn't look ahead and see what will be the effect of taking certain action at current time on performance. So I think the right solution to your problem is to design controllers that co-optimize safety and performance. And there are recently there have been some sort of formulations of dynamic programming, which optimizes both of these requirements simultaneously. So it will be interesting to see if those type of controllers naturally trade off these two things.
We can't really have 100% safety, right? We have to compromise on.
Yes. So absolutely. So I guess that's there's this trade-off between computation and the level of safety assurance. So I guess the trade-off I'm making is along that curve where I'm willing to give up certain percentage of safety in order to have a more scalable computation. Yes.
I'm just curious, is there like any research that you know of that goes into like levels of guarantees within safety? Like, is there like tiers that happen?
That's I would imagine so. I personally don't know, but I know that at least all the companies that I've worked with, they never think of the safety in terms of absolute sense, which is 100% safety. They have their levels of safety, but the ways of computing those levels are a little bit ad hoc or heuristic ways. But they have levels. So they sort of for example, collisions have different severity associated with them. And so they would call it like, okay, this collision is really bad. So there's almost a hierarchy of safety levels they care about. I haven't seen personally much work in academia on that front, but that's an interesting question. Yes.
So I don't want to talk too much about Waymo proprietary things, but you had the example of the really interesting example of the adversarial situation where you're actually convincing the oncoming car to squeeze in. So I was just wondering, in a controller like in that situation, is that symmetric about if you take a human and a Waymo and you swap each controller out, does it work Waymo to Waymo, human to Waymo, and in reverse? Is it symmetric?
That's going into a very interesting game theory land. Here I'm conveniently assuming that the information is symmetric. So I'm assuming that I can not only the cars are symmetric, but I can control both cars. That's not true. When the oncoming traffic is you driving, I can't really control your car. The reason I'm making that assumption is because I'm assuming that when it comes to collision avoidance, there is a certain level of cooperativeness between the drivers, which is maybe you also don't want to collide with me when I'm.
At first, when you see that situation, to me it seems really worrisome. But on the other hand, maybe people's avoidance of those things is actually really robust. And just as robust as many studies.
You will be surprised. So there's a whole distribution, and I think before we get to this planning level, there is often a behavior level classification that happens. So looking at the past trajectory of that vehicle, for example, we classify whether this car is behaving more like an adversary or behaving more like a cooperative car, and based on that, our planning strategies are different. It doesn't necessarily being done in these classification levels that I said, but there's some behavior planning that is happening, which then decide how should we try to nudge around this car. So it's a little bit more complicated behavior level.
Those Waymo cars in the city do seem to be, they're not necessarily shy, right? They've gotten quite.
They were very shy. Okay, I'm being recorded, so I'm gonna stop here. I'm gonna stop here. we can chat offline.
This is for happy hour.
Yeah, I think so.
Is there one more question or no? Thank you so much.
All right, thank you.